Welcome back, my dear friends. A very good morning, good afternoon, good evening to all of you wherever you are in this part of the globe. And as you know, this is the DADM 3, which is Data Analysis and Decision Making 3 course under NPTEL MOOC series. And you are all aware, so please excuse me if I am repeating. This course total duration is 12 weeks, which total contact hours is 30 hours, and which when converted into number of lectures is 16 number. That means each lecture is for half an hour, and considering the fact that each week we have 5 lectures, each being for half an hour. After that we have an assignment. So, if you see the slide, we are in the 5th week 24th lecture, that means the 24th and 25th will basically end your 5th week, and all of you have already taken 4 assignments. After this you will take the 5th assignment after the 25th is over, and after the end of this course you will basically have the final examination to take for the evaluation. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. Now, in the last fag end of the 23rd lecture, I was repeating one of the slide which I have already discussed. The reason being that it was a very generic nature of how you write the problem. You basically have a set of objective function, and we initially for all these number of days we considered that there was only one objective function with some assumptions like linearity of the prices, proportionality. They can be broken down into a number of infinite small decision variables, all these things, and the constraints were also not probabilistic, they were all deterministic. If you remember, I did repeat it time and again. The constraints were specific to either the greater than type, less than type, equal to, and equality basically came up later as we added the slack and the surplus depending on how you formulated the problem. We also considered that the x's were greater than 0 as per the assumptions. Now, generally whenever you are trying to solve the problem, in one of the problems we saw that the slack and the surplus technically which should have been 0 are not 0, in the sense that some amount of slack or surplus would be left in order to basically attain the maximum, which is the basic feasible solution which was optimal. So, we will try to basically dwell on that about sensitive analysis and all this concept as we go ahead. So, again this slide comes where we are considering an optimization framework of a maximization or minimization, whatever it is, of only one I is equal to 1, you will basically have a single objective, and if it is a linear, it will be a linear problem. And the constraints which you are considering, like if you consider the constraints which were there for factory 1, 2, 3, which is plant 1, 2, 3 or machine 1, 2, depending on how you have formulated the problem, the constraints were basically deterministic in nature, and as it says like Gj's or Hk's are basically the constraints depending on the set of variables which is x. Here all we are taking are x or d. D is basically the deterministic constraints and deterministic parameters, and p is the probabilistic parameters. They are all vectors. The number of vectors would denote the variability in the problem. So, x basically be of dimension n, it means there are n number of variables which need to be solved to arrive at the problem at the solution. Now, when you are considering Gj's are greater than, equal to, less than, so it obviously means that it would be there would be some slacks or surplus depending on how the problem is formulated. But the issue of basically trying to have another set of constraints k in number, would k is equal to 1 to capital K and j is equal to 1 to capital J, would basically be segregating the sets of constraint into some which are probabilistic and some which are deterministic. Now, this will come later on when we give concept to the diagrams, which I will come within few minutes. Now, we have the linear, nonlinear and objective functions I is equal to 1 to capital I. So, if it is linear and I is 1, we had whatever we have been discussing till now, the linear objective function optimization problem, the simplex method we have been utilizing. And in case if there is no probabilistic constraint. So, if you see the third bullet point, that hk xdp, and we are in here in this problem we are considering the red color to signify the probabilistic nature of either the decision variables or the parameters, exogenous parameters, or the input variables also. If x is not probabilistic, or p is not probabilistic, or c is not probabilistic, obviously all of them would be deterministic, and you will basically solve the problem as given in the simplistic sense, whether the linear programming or the non-linear programming. And combined, you have the constraint as greater than, less than, equal to, where on the right side you have the bj's, j is equal to 1 to capital J. So, b concept I am taking is exactly as it was there in the optimization problem we had solved, A x is equal to b. Now, if d, p and c are all deterministic, then the set of constraints basically becomes capital J plus capital K, and that is exactly equal to the number of rows and the number of columns which you have for the problem when you have basically solved using the Gauss-Jordan concept. Now, why I have considered a little bit beforehand the probabilistic one is to give an intuitive feel that what we will be doing later on, and in a very simplistic way was to consider that the parameters which are not under your control and some of the decision variables which you want to take have some distribution. Like say for example, you are designing a car and you know that the weight of the door or the weight of the chassis, whatever you want to design, or the weight of the roof of the car is under your controls, which is a parameter which is given by the designer, and your main decision problem is basically to find out the cost, reduction in the cost, minimum cost. So, these would be set of deterministic parameters, while the parameters which are probabilistic, which are not under your control, which you know has to be considered or they have to be considered in the problem, would be say for example, the speed of the wind, or say for example, the road conditions. So, all these things would be parameters which are non-deterministic, probabilistic. Here x, t, p, b, c may be continuous, discrete, integer, binary or positive, or whatever the framework of the domain of this x, d, p, b, c would be depending on the scope of the problem. And as I mentioned, which I am mentioning again, that the I value would be 1 for a single objective function, would be more than 1 for a bi-objective. If it is 2, it is a bi-objective problem, for higher it will be more than 2, which is a multi-objective problem. Now, where the actual interesting part comes up is we will discuss in the diagram. So, in the simplistic case of probabilistic optimization, this would be an optimization technique where the model, or when we solve the model considering that there is some data uncertainty. Data uncertainty, as I mentioned in the car design problem, it can be say for example, of designing the dam, it can be for the designing of the portfolio, it can be designing of heat chamber or cooling towers in mechanical design or civil engineering design, it can be designing of say for example, the amount of money you are going to spend for investment in government projects where the returns are flexible, which are not under your control depending on the market conditions. So, there can be different examples based on which we can understand the problem. So, you will model the optimization problem with data uncertainty, which I mentioned, and when you are trying to solve the problem, it is not deterministic, you will basically take some robust and reliable solution. Robust and the word reliable is what we will be coming back in the deterministic sense also. We will consider some robust and reliable solution. Reliable means to what degree they are true, or with what certainty we can say that these answers will be coming out, or to what level of confidence can I say yes, those values would be true for the problem I am going to solve. And robust in the sense that any perturbations in the variables and then whether the deterministic one or the probabilistic one would keep our answer as close as possible to the deterministic value which you want to find out, such that we are certain with a high amount of confidence that the answers would be almost the same even if the external parameter values are changed. So, that what obviously would be the answer, because in case say for example, we are designing a car and the cost factor is coming out to be depending on whatever different type of materials we use, and if the information set from the outside like the wind speed will vary largely or the road conditions would vary largely, even if that factor is there, and if the costs are as low as possible and they are in and around the value which you have found, then we are certain that our answer or our optimization problem has been very robust, in the sense that we are able to give good results as decided. We would definitely try to find a solution, and that may not be very applicable for the deterministic sense. We would definitely like to find out solutions which do not violate the basic the feasible region which you have. That means, the problems which you want to find out, the solution which you want to find out would be one of the solution along the corner spaces, and if it is not, obviously we will try to check whether they are violating the constraint, whether they are out of the feasible region. So, that should not happen, like yes, the external factors are there, but that should not affect the answer or the feasible point to be infeasible, now become infeasible. So, that has also to be looked into. We would basically find an objective function, an optimum objective function, considering the uncertainty in the initial case, and then slowly relax the uncertainty later on and check how the answers in the uncertain case, considering probabilistic variables, probabilistic p values, probabilistic constraints, how they affect the deterministic answer. And we will consider both at the same time, such that both the variables, decision variables as well as the parameters are uncertain. So, obviously, there would be a joint distribution. How we will model that, we will see later part in this course. Now, the available classical methodology based on which we treat data uncertainty would be sensitivity analysis, which we will consider in few slides later on, either in the 24th lecture or in the 25th lecture. And else we use stochastic programming, robust optimization, reliable optimization based on how we have been able to model that problem, considering whether distribution is one of the factors we are going to consider, or it is basically distribution would be there, but we would not consider any parametric form for that distribution as such. Now, whenever you are doing this probabilistic one, and we will come later on this sensitive one. Sensitive one is basically how sensitive the answer is with respect to the perturbations of the constraints or perturbations of the variables or perturbations of the parameter values. So, the probabilistic nature of the optimization comes from two different sources: set of the variables which is x and p, and how they are changing, and how the parameter values, external parameters p's are changing. And it will also depend on the input parameters. So, if you remember, the C case were also non-deterministic. So, how they are changing and what effect they have on the constraint would also dictate, because if the right hand side C case are changing, obviously it would mean that the constraint space or the feasible region would also be changing, which means that you will have different sets of interior points based on which you will do a search, in the very simplistic sense what I am saying. Now, when we come to the optimization problem, so there would be some philosophical change how we model it. So, in the general, the probabilistic so the problem or the model which I have discussed in a very general sense was the deterministic one. Now, if you bring probabilistic sense into the optimization problem, then you will basically have an optimization where x and p are non-deterministic, hence they are shown in red color. That means, the decision variables also is not known with certainty, and the parameter values which are affecting our decision model is also definitely not under control, and that is there is a distribution. If we know, it is well and good. If you do not know, then you have to basically assume something and proceed accordingly. Now, we divide the total constraint into two sets. So, initially it was deterministic, you will only consider the deterministic part. So, they were the total number of variables would be, as I mentioned, would be capital J plus capital K. Capital J is the number of constraint which are being considered as per the slide here are deterministic, and the capital K number of constraint which are now probabilistic. Now, here is where the interesting part is. If they are probabilistic as per the concept, so obviously the right hand side K, Ck's are unknown. So, they are changing, that means they are perturbing. So, if their perturbations are there, the movements are there, they are shifting either outside or inside based on the initial surface which you have. So, that means either straight line or a plane or a hyperplane, depending on how the problem has been formulated in one dimension, in 2 dimension, 3 dimension or higher dimension. But now a probability will come, or a chance, or the level of reliability which you want to assign. Now, this concept of reliability would be formulated in 2 fronts. 2 fronts is that if we consider the distribution per se to be normal, which we will consider to make our life simple, then we will basically consider the perturbations in such a way that we will include normality and solve the problem, which I have already told many times, but I will still repeat. So, if you see the set of capital K number of constraints here, which I am highlighting, there you have a reliability beta. So, how reliable you are, it is beta 1, beta 2, beta 3, which is 90%, 95%, 97%, 99%. Higher and lower the values of beta will give you how reliable you are, how less reliable you are. Now, think from the normal distribution. So, if you consider the normal distribution, and from my side, if I am considering the values are increasing. So, x is basically from minus infinity to plus infinity. I am not considering standard normal, and the probability distribution for x is given. The middle value is the mean, median, mode is mu suffix x, which is the mean value, and obviously there is a standard deviation. Now, if I consider this highlighted part and I write like this. So, I am using the color blue. So, generally we know probability PR of capital X less than equal to small x if this is equal to alpha. So, what we do is that we have the distribution is a univariate normal distribution, it can be converted into multivariate normal distribution also, the problem would not be that difficult. So, you can consider some x value, and you want the x is a realized value, what we can understand, and we want that. So, I will use color highlighter green. So, I would basically consider capital X is on to the left hand side or right hand side, depending on the problem has been formulated. So, this less than type would come for the case when you have this less than type. So, in case it is greater than type, let me use another color. So, this is greater than type. This is the greater than type, and in that case it will be assume this, where the problem formulation would be of the greater than type. So, when you are considering the normal distribution, life is very simple. So, what you will do is, I will just write it here only. So, we will consider probability x minus mu x by sigma suffix x. So, this sigma suffix x or mu x, what I am considering is in the univariate case. corresponding to the fact. If you have the multivariate case, you can convert using the multivariate normal distribution or whatever the dimension is, and less than equal to the small x mu x divided by sigma x is equal to alpha. So, you are basically transforming from the x distribution to the z distribution, and when you transform, what you are doing is that you are converting this x minus mu x divided by sigma into capital Z, which is the standard normal deviate, and this one x minus mu x, small x minus mu x by sigma x as small z, the real s value. So, this would mean that I would basically have the distribution standard normal, find it out, plug in and finish my answer and solve the problem. Now, the question is, I am coming to the sensitive analysis, but question is that what happens if the distribution per se is not normal. So, it can be anything. How do I find out? So, either you do simulation, that means you simulate in such a way that you find out how many number of times out of 1000 simulation, millions, 1 million simulation, 2 million simulations if you do, how many times this is valid. Based on that fact, you will find out the alpha value, because alpha value is not changing. The overall area which I have here is basically alpha, and the area onto the right hand side, which is the saffron color, is 1 minus alpha. So, that because the total sum is always 1. So, you will always ensure that. Now, in the simple univariate normal distribution, you can either simulate or use simple transformation to convert into a normal distribution and then solve the problem. But in case if it is a multivariate non-normal distribution, you will basically have to simulate and basically find out the distribution on an orthogonal plane for each and every of the x's which are non-normal. Try to find out their orthogonal transformation in the non-normal surface, and then find it out to solve the problem, which I am going to come to that later on. But how would it look when you are trying to solve the deterministic part, then the normal distribution part, with considering sensitivity analysis and there is a perturbation, then the case where you have the non-deterministic part of the perturbations. So, this would be discussed within few moments using simple diagram conceptually, and then I will basically come to the problem solution. Now, I will spend some time in this diagram. It may be a little bit more involved, and as I go step by step, but I will try to basically go into the details. So, first consider it is a only 2 dimension problem, and you have along the y axis one of the variable which is x2, and along the x axis you have one of the variables which is x, or along the y axis you have x1, sorry, along the x axis you have x2. So, these are the 2 variables only, and let me draw it before I come to this diagram. Let me draw it. So, this one, so I will create 3 blank slides and then proceed. So, I basically draw. First, let me start with the linear optimization which I have already done. So, this is a 1 dimension x1 and x2. So, let me plot x2. The way you draw x1 x2 does not change the concept as such. So, your space which we have been already doing, this was one constraint, the second one and the third one. So, the points based on which you will do your movement was A, B, C, D and E, and your feasible region, that so this was the feasible region. I will mark this with green color and then basically go into trying to give these perturbations in such a way. So, it is easy for all of us to understand. So, this is the feasible region which you have. Now, what happens? So, consider this green line. So, this is the point, consider this is the one of the constraint. So, that was one of the sets which was in Gj and Hk, if you remember. Consider that is either Gj or Hk and both are deterministic. Now, assume that it is now probabilistic due to some reason, x is variable, varying, p is varying, whatever. So, if I look at it from the point of view if it is a normal distribution, then the distribution, the perturbation in the univariate case would look like this. So, it is perturbing. So, if I have a perturbation or movement for this constraint ED, it basically normal. Or if I have a perturbation, say for example, for BC constraint, here normalities have been drawn in such a way in order to basically differentiate there is a variance difference. Now, if normality is there only for one, I solve the problem using probability x less than equal to small x is equal to alpha or greater than alpha, less than alpha, and I am able to proceed. But what happens if they are combined? So, in the case they are combined, there are two scenarios. I will come back to this diagram once again. There are two scenarios. Scenario 1, where the variances are same for the 2-dimensional one, and scenario 2, the variances are different, and another concept would be if they are not orthogonal to each other, if they basically merge. So, I will basically try to draw it using the diagrams, explain it, and then proceed to solve the problems later on using the concept of very simple sensitivity analysis for the deterministic case, and then go into the probabilistic case later on once we come to the robust and reliability problem. With this, I will close this class and have a nice day, and thank you very much.